Okay, good morning, everyone, and welcome to the second in our guest speaker series for SSP 2021 Astrophysics New Mexico Tech campus. I'd also like to welcome the ONL campus, who's also here for the guest speaker today. And as always, I am only here to introduce NMT team number 4, who has prepared an introduction for our guest speaker.
Today, we have the pleasure of introducing Mr. Aguirre y Arcas, an extremely accomplished software engineer, software architect, and designer. In 2003, Mr. Aguirre y Arcas founded Seadragon, which was later picked up by Microsoft Live Labs. He joined Live Labs in 2006, where he became one of the creators of Blaise, a groundbreaking program used to convert digital pictures into interactive 3D models.
In 2008, Technology Review magazine recognized Mr. Aguirre y Arcas as one of the world's top innovators under the age of 35. He has given several TED Talks, one of which was named as Bill Gates' 10th favorite TED Talk of all time. As a distinguished engineer at Microsoft, Mr. Aguirre y Arcas became the architect of Bing Maps, the online mapping service that is part of Microsoft's Bing Internet search engine.
Mr. Aguirre y Arcas also founded the Artist in Machine Intelligence program at Google, a program that fosters collaboration between engineers and artists to create art using machine intelligence. Currently, he is a leader in machine intelligence for mobile devices at Google, where his team works with deep neural nets for machine perception, distributed learning, and connectonics, research that studies the brain's connections between cells. Also, as a fun side note, he inspired the character Elgin in the best-selling novel, Where'd You Go, Bernadette? With that being said, it is an honor to welcome Mr. Aguirre y Arcas.
Thank you all. That's an extremely kind introduction, and I'm really excited to be back at SSP virtually this year. I don't know. I'm hoping that maybe next year it won't be virtually. I'm going to go ahead and share my screen so that I can show you slides. And before I do that, I want to encourage the question askers to please break in anytime and with questions or comments. I'm happy to take things as they come, but I probably won't be able to see you once I've got the slides up. So please break in via audio. All right. Can you all see my screen?
Yes.
Very good. So it's probably not worth it for me to go through the bio, because you all have already done a good job of saying who I am. But I will mention a couple of things. I grew up in Mexico City and moved to the US for high school, and I was actually in SSP in 1991 at the Thatcher School in Ojai. It was really a sort of pivotal experience for me. It was when I felt like I finally met my people. So it's exciting to be back here and to see your generation going through the same experience. Eventually, I went to Princeton University and studied physics there, and then switched into computational neuroscience, which I'll talk about a little bit because that had some bearing on my moves later into AI and machine learning, and the rest I think we've discussed. I've been at Google since 2014, leading a team there working on AI, and I want to talk today not just about AI but about ethics, because this is a pretty hot topic nowadays. I think in technology and in society generally, and in AI specifically. And I'm actually worried about some of the ways in which the ethics conversation is happening, because I think it's a critically important one. It's also one that we should ground in both what the technology really is and where it is and what it means for us, and in maybe a more grounded sense or more grounded understanding of ethics and what that means than I feel like often gets billing these days. So I'd like to dedicate maybe a little more of the talk than than I did last year to talking about those things, and then we'll move from that into AI. And I hope that you'll see parallels between the ethics discussion and the AI discussion as they knit together, because I think in many ways, sort of thinking about these topics, has actually paralleled, if they parallel each other in ways that are not necessarily obvious. So what are ethics? And I'm going to give this with a somewhat neuroscience and machine learning sort of slant. So first, there's the difference between morals and ethics, or a moral precept and an ethical code. This is, kind of what you get if you Google it. A moral precept is an idea or opinion that's driven by a desire to be good. And an ethical code is a set of rules that defines allowable actions or correct behavior. So what you might be gathering from that is that they operate at different scales. What I'm showing here is Adam Smith's theory of moral sentiments from the 18th century. And Adam Smith is most famous for, as sort of the father of capitalism, but this is an earlier book that he wrote, and I think in some ways a more profound one, Moral Sentiments. This is from his introduction to that book. How selfish soever man may be supposed, there are evidently some principles in his nature which interest him in the fortune of others, and render their happiness necessary to him, though he derives nothing from it except the pleasure of seeing it. As we have no immediate experience of what other men feel, we can form no idea of the manner in which they're affected, but by conceiving that we ourselves should feel in the like situation. So, neglecting the fact that he's talking about men and not necessarily about old people here, he's talking about empathy, and the idea that moral sentiments are about relationships, and they're about feeling empathy with other people, and thereby wanting good for them and not only good for yourself. That's sort of the first step. And this builds on top of a really kind of fundamental individualist idea that is popular in evolutionary psychology, called the 4 Fs, which is the most basic impulses that a living organism is traditionally held to have. So these are the primal drives that animals are supposed to have: fighting, fleeing, feeding, and mating. If you're an evolutionary biologist, then you imagine that this is sort of looking out for number one. This is the fundamentals. When you add to this moral sentiments or empathy, then you get something relational. You're not only concerned with whether you have enough to eat, but also with whether your child, your family, your friends, your kin, your kith, whether they have enough to eat as well, for instance. So you can see that we build up from this kind of individual idea about survival and basic drives and impulses to empathy in the Adam Smith moral sentiment sense. So what are the needs of others that that you have relationships with, and then there's a third layer to this cake, which is the eusocial layer. Not just the social layer, but the eusocial layer. What do I mean by eusocial? This term is often used in the ethology of insects, and in studying ants and bees and other such species, because ants and bees and other kinds of social insects don't have individual relationships. They don't have first names, if you like. They only have last names, and so eusociality is about society in a sense that is decoupled from the idea of individual empathy or individual relationships. They certainly have a sense of membership, of tribe or group, right? So entire ant colonies can be at war with each other, for instance. But when an ant, sort of communicates with another ant, they do that via pheromones and chemicals. And those chemicals say, is this other ant in my hive or colony or not? And if you like, the moral sentiments of anonymous societies like that one are what eusocial behavior looks like. So yeah, ants can cooperate at massive scales, but still have massive wars with each other. The Argentine super colonies are kind of the famous example. There are several very, very large super colonies, one of which spans much of North America. And if you happen to find a spot where one super colony abuts another, you'll see, for all of the cooperation that exists in one super colony, sort of carnage and warfare right at the interface where two super colonies touch each other. It's quite fascinating. Now, we have, as humans, the same kinds of super colonies or anonymous societies. So, if any of you have a driver's license or a passport, or, if any of your parents have a union card or anything of that sort, that tells you that we have anonymous societies too. So, you can be a member of something like a country, a company, a union, a religion, and so on. And that means that you will have certain obligations and desires and so on that are about that group, and that don't rely on individual relationships. When we believe in rights for certain groups of people, or for that matter, if I just walk into a coffee shop where on the corner where there are a bunch of other people, the fact that that I kind of know what the expectations are, that there are certain sort of social norms and mores and expectations about rudeness, kindness, fairness, etc. In that environment, despite the fact that I don't know anybody individually in that coffee shop. That's a function of our eusocial nature. And this is, by the way, something very, very different that we've got that the other great apes don't. Chimps don't have coffee shops. Right, a chimp walking into a coffee shop where they don't know any of the other individuals will freak out because without those individual relationships, there's no sense of expectation. Is this an enemy, a friend, in group, out group? No such thing. So Jonathan Haidt famously has characterized us as 90% chimp, 10% bee. I think that might be at least 50-50 instead, or maybe even 10-90 the other way around. We have this chimp nature, which is about individual relationships and Adam Smith's kind of one-to-one, empathic kind of stuff going on. But we also have these eusocial properties as humans that are, that we actually have to look to social insects and other animals that are very, very far from us in the tree of life to see other instances of. So I think that's kind of core to what makes humans interesting and different. This is a case that Mark Moffat makes in this book, The Human Swarm, which I think it's a very strong book. So if we just sort of, I've played around with the idea of making spreadsheets of different sorts of entities that we model as humans, ranging from human individual up to the entire planet. When I say entities of this kind, I'm talking about entities that are intelligent in one form or another, entities that we model as having, as being able to be harmed, for instance. So this is a table of whether things can be harmed, not just a human individual or a non-human organism, but an artifact, a family, a neighborhood or a physical community, an online community, a reproductive lineage, a corporation, a political party, a social network, a city, a tribe or nation or country, a religion, even an idea like democracy, for instance. We imbue all of these things with a certain level of agency, of who-ness, if you like, and we can think about whether these things can suffer biological harm, can they suffer economic harm, can they suffer a political or social or cultural harm. And you see I've got some 0.5s, which is like not sure, maybe, and some zeros and some ones, quite a few ones. Including cultural harm in almost all of these cases. You can get a little more sophisticated still and ask things like, can this entity be a defendant in a U.S. court? Can it learn through corrective justice? That is through feedback. Can it be deterred by example? Does the idea of retributive justice or punishment work? Can it experience pain? Does it construct social models? Does it have awareness and attention? What I'm trying to get across here is that, the idea that individual humans are the only intelligent things on the planet is not only wrong in the sense that there's lots of animal intelligence out there, but also in the sense that there are all sorts of larger structures, including, companies, programs like SSP, countries, and so on, that also are entities. They're also non-human entities that are made up of humans, but that have their own dynamics. Just as humans are made up of neurons, many of these things are made up of humans, among other kinds of components as well. So we live in this very complex and multi-scale web, and I think that we have done a little bit too much of of kind of favoring or thinking, in a very individual way about humans as isolated beings, when in fact we are part of this nested set of scales with all kinds of entities already in it. So, the idea that if we build a computer with AI, it's the first intelligent thing that exists outside of individual humans is completely wrong. All of these other entities are intelligent as well. So, so this is what the ladder looks like, right? Basic drives at the individual level, empathy at the moral sentiments level, and ethics at the eusocial level. When we talk about larger rules or principles, we often are talking about that top level. Now, not everybody historically has agreed about this top level. Margaret Thatcher, in this rather famous interview in Woman's Own magazine in 1987, said, "There's no such thing as society. There are individual men and women, and there are families. And no government can do anything except through people. And people must look after themselves first. Themselves, that's the 4 Fs. It is our duty to look after ourselves and then also to look after our neighbors." Our neighbors would be that Adam Smith moral sentiments stage. So basically, she's denying the idea that humans are eusocial, that we have society, that that there are these larger things other than you and your friends. In other words, she's saying we're nothing but chimps, and I believe that that's very obviously wrong. Otherwise, there would be no coffee shops. Now, one of the places where I think we go wrong is that we tend to talk in terms of utility when we look at basic drives. Utility meaning a score somewhere between bad and good. Hungry, bad; fed, good. So it's just kind of like a scalar value at the basic drives level. And at the ethics level, when we start to ladder our way up and we think about eusocial stuff, we tend to think about rules. That's in most definitions of ethics, a set of rules that allow for for ethical behavior at larger scales. And both this idea of utility and this idea of rules have actually been proven not to work. But that memo seems not to have been received by most moral philosophers or scientists or ethicists or people working in these fields. So I'm going to give you some of the evidence about how it is that both utility and rules have been proven to fundamentally be broken, not work. Both rules and utility don't work, and also there's maybe an even bigger problem here, by the way, which is that given this layering in which you have smaller entities collecting together to become larger entities, it's actually impossible for these levels to align as well. In other words, if you want things to be good for individuals, but then you have individuals working collectively, there are always going to be some hard trade-offs there in the individual versus collective. You can't actually get alignment between the levels, so it's a problem. First, let me give you some of the evidence against utility. So this is a somewhat gnarly study from 2002, 2003 by Danny Kahneman, who is an economist who won the Nobel Prize, and a couple of collaborators, called Memories of Colonoscopy, a randomized trial. So colonoscopy is a very unpleasant procedure that anyone over 50 is probably familiar with, in which an uncomfortable tube gets stuck up your butt in order to see if you've got cancer, and you're supposed to do this every now and then. I hear it's become better, but in 2002 it was extremely unpleasant, and Kahneman and colleagues did an experiment in which people had a pain dial from 0 to 10 that they would move around, that they would move as this procedure is taking place, and they did a kind of a weird intervention. They took they took half of their population of people undergoing colonoscopies and added several minutes to the end of the procedure, in which the pain would slowly get ramped down, whereas in the other half of the patients, the thing would just get removed all at once. So like you stop the procedure. Now, given the idea, if you have any kind of sense that pain is something that adds up, right? Pain or discomfort is additive, then there's no way that adding 3 minutes to the end of the colonoscopy could make anything better, right? It will necessarily make things worse. How much worse it makes it depends on how you integrate, right? How you kind of add up that pain or discomfort over time. But it turned out that that adding the 3 minutes actually made things better. Quote from the paper: patients' memories of the past may influence their decisions about the future, yet memories are imperfect and susceptible to bias. Half the patients had a short interval added to the end of their procedure, during which the tip of the colonoscope remained in the rectum. Sorry for the imagery here. Pain during the procedure was measured with a 10-point intensity scale. Memory following the procedure was measured using both a rating scale and a ranking task. As theorized, patients who underwent the extended procedure experienced the final moments as less painful, rated the entire experience as less unpleasant, and ranked the procedure as less aversive compared to 7 other unpleasant experiences. So this is pretty weird because, you know, if you don't have additivity, right? If basically something unpleasant, you know, can actually become more pleasant by adding a little bit less unpleasantness at the end of it, then you've just broken the idea of utility in a fairly fundamental way. Now, Kahneman and colleagues called this irrational or biased, and that actually, I think, is a mistake. That assumes a ground truth of pain equaling harm and being additive. And there are really no grounds to assume that. Our evolved neurochemical and cognitive systems, that includes sensitivity to derivatives and preference for narratives versus the integration of a pain signal, those, you know, have presumably served us pretty well over the past 350 million years since we've had a brain. And you know, I would guess that a pain additive approach would have served us less well, since that's not what we've evolved to do. You know, there's certainly no problem with doing integration in our brains when that's the right thing to do. So oculomotor reflex, which keeps our eyes trained on a subject when we move our head from side to side, does integration beautifully. But that's not what we do with pain. So probably there's a reason. So, you know, while the work of behavioral economists like Kahneman is valuable and revealing, the need to frame it in terms of debunking rational behavior, quote unquote, maintains, in my opinion, without justification, an imaginary gold standard of what they call homo economicus, or you know, a person who is rational according to some idea of utility. Now, one of Kahneman's collaborators, Amos Tversky, way back in 1969, published a paper that I think is you know, absolutely the death knell for these ideas of utility, and it's this paper called Intransitivity of Preferences. So the idea here is that, you know, if you have anything like a scalar utility, and you know, things A, B, and C have a utility, then if A is better than B and B is better than C, then A must be better than C. And this is just kind of like the most basic thing about right, about it's the triangle inequality, essentially. I'm sure you've run into it before. But it's actually very easy for Tversky to set up situations in which people can be made to prefer A to B, prefer B to C, but not prefer A to C. This is the same, you know, bias about bias, incredulity. Tversky writes, transitivity is one of the basic and the most compelling principles of rational behavior. For if one violates transitivity, it is a well-known conclusion that he is acting, in effect, as a money pump. Suppose an individual prefers Y to X, Z to Y, and X to Z, it is reasonable to assume that he is willing to pay a sum of money to replace X by Y. Similarly, he should be willing to pay some amount of money to replace Y by Z, and still a third amount to replace Z by X. Thus, he ends up with the alternative he started with, but less money, right? In other words, you could just walk somebody around this cycle over and over and just pump money out of them indefinitely, you know, given such an intransitivity and preferences. So, you know, that tells us that this is a fundamentally non-economic, you know, and non-utilitarian model of how people work, and people in fact work this way. So, so yeah, rational, this idea of rational owes a lot to economics, in which a single reward, money, can be quantified. And if a behavior is efficient or optimal, then it's rational. So burning dollar bills, or giving things away for free, or offering unnecessary discounts, all of that would count as irrational behavior according to economists. But of course, people do all of these things all the time. Now, here's a final piece of evidence that I think is important and powerful. This is also an oldie but goodie. It's the 1951 PhD thesis of Kenneth Arrow, who also won the Nobel for this work. And there's a theorem named after him, the Arrow impossibility theorem, or actually a series of theorems. And it's a generalization in a way of what Tversky found. He basically says that it's easy to construct intransitivity from voting for 3 people among 3 choices and that more generally, it's impossible to build a fair voting system. So Arrow writes, in a capitalist democracy, there are essentially two methods by which social choices can be made. Voting, typically used to make political decisions, and the market mechanism, typically used to make economic decisions. The methods of dictatorship and convention are or can be rational, in the sense that any individual can be rational in his choices. Can such consistency be attributed to collective modes of choice, where the wills of many people are involved? So in other words, can you get a collection of people and have them vote in some way, any way, right? Any way that they can sort of pool their desires and have something rational emerge from that. Now, by rational, he meant that there should be three properties that seem pretty straightforward. First one is, if every voter prefers X to Y, then the group prefers X to Y. That seems obvious, right? The second is, if every voter's preference between X and Y remains unchanged, then the group's preference between X and Y will also remain unchanged, regardless of the voter's preference between other pairs like X and Z, or Y and Z, or Z and W change. And finally, there's no dictator, meaning no single voter possesses the power to always determine the group's preference. Now, what Arrow proves is that it doesn't matter what kind of a voting system you make, you can't satisfy all three of these constraints. He does this kind of clever proof in which he begins with a set of all possible voting systems, removes the ones that violate, the first principle, then removes the ones that violate the second principle, then removes the ones that violate the third principle, and you end up with the null set. So there is no such thing as fair voting. It can't be done. Now, this is a real problem, because even if you began with the idea of individual rational actors, once you have them acting together, basically they can no longer be rational. So we're really screwed if you have this kind of economic idea of utility. Peter Eckersley, just a couple of years ago, sort of wrote up the implications of this for AI value alignment, impossibility and uncertainty theorems in AI value alignment, or why your artificial general intelligence should not have a utility function. It's a good read, and there have been a number of papers along these lines that have connected these classical results with various kind of AI fairness questions, and made exactly the same conclusions, that the idea of making fair AI or ethical AI is at its core impossible. What you can do is at best think about trade-offs, think about forces or pressures that push it this way and that, but that some idea that by following some set of rules or by optimizing some utility, fairness can result. It's actually a fool's errand. It's not possible to do. So I'm going to shift at this point to talking about AI. I know that was a little bit abstract, but I hope that that you've followed it and that it makes some sense. And again, please break in with questions as I go. Now, original ideas about intelligence were rule-based, and also embedded this idea of rationality right at their core. I would say that this story, I mean, we can push it back to the to the classical period or earlier, but I'm going to choose to begin it with Gottfried Leibniz in 1666, one of the inventors of calculus, as you all probably know, along with Newton. Leibniz was a very interesting fellow and a polymath, and invented or dreamed up all sorts of things, among them binary, by the way. He imagined also that that intelligence or computing could be rational, and he also imagined that it might be possible to make a calculus of ideas that would allow for any kind of statement, whether it's about not just about math, but about ethics, about religion, about philosophy, about politics, to be turned into a mathematical statement. So this fantasy, basically holds that there is a way of correctly answering questions, or deciding which of different possible alternatives is the better one, through a reasoning process, through a mathematics-like reasoning process. And this idea that intelligence and reason and rationality and logic can all be equated with each other has had a long shadow When we think about the way, really smart AIs like, Data in the old Star Trek, get depicted as these kind of hyper-rational, computers that thereby can reason their way out of anything, and can decide which of two alternatives is really better, despite the irrationality of a lot of humans. That's the shadow of the same idea, right? That somehow by calculating something precisely, you can get to a rational as opposed to an irrational or flawed answer, the way humans have got. The way Leibniz put it in his Dissertatio de Arte Combinatoria in 1666 is, if controversies were to arise, say between philosophical statements or something, between two philosophers, there would be no more need of disputation between two philosophers than between two accountants. It would suffice to take their pencils in their hands, to sit down with their slates and say to each other, with a friend as witness if they liked, let us calculate, calculemos. So that was the fantasy. And by the way, his invention of binary was actually part and parcel of this idea. So he made the relationship between binary, divine creation, and logic, in the sense of every predicate being true or false, a 0 or a 1, and that calculating in binary would be the way to carry out this kind of logical calculus that he imagined. So this same idea, permeates, it kind of reverberates down through centuries. Leibniz had this idea. The Mechanical Turk, the famous chess playing Turk, which was a kind of a hoax that had a human player hiding inside, also was an inheritor of this idea in a certain way. This is kind of famous in the sort of annals of the history of AI or fake AI. But the reason I list it is because it's supposed to play chess. But what I think is less known about it is that often after playing a game of chess, the hoaxer would put a kind of Ouija board in front of this mechanical chess player, and then people could ask it questions, and it could answer by moving the pointer around on the Ouija board, and that wasn't even remarked on, because of course if something is intelligent enough to play a strong game of chess, then it's intelligent enough to answer any question as well. Right, which betrays that same kind of logical bias, right? That a logical game that you can win or lose using by following rules and by optimizing utility or something, means that you could surely answering some gossipy questions that is no more complicated. George Boole, after whom Boolean logic is named, 19th century. The book in which he invented Boolean logic is called The Laws of Thought. And imagine that thinking is done by logical operations as well. Russell and Whitehead, who wrote the Principia Mathematica in the early 20th century, believed that everything in math could be boiled down to logic. And Ludwig Wittgenstein, the philosopher, also early 20th century, started off by believing that every kind of statement could be boiled down to a kind of logical calculus, just as Leibniz had imagined. The pinnacle of this kind of logicist idea was this very important paper in 1943 by Warren McCulloch and Walter Pitts, called A Logical Calculus of the Ideas Immanent in Nervous Activity. So McCulloch and Pitts were early neuroscientists, basically, and they had noticed that neurons in the brain have all or none excitable behavior. They either spike or they don't spike. And they made the connection between that and Boolean logic. And they said, well, the brain is full of these neurons that either fire or don't fire. And so maybe they're carrying out logical operations. And so they started to make these diagrams like you see here. Those triangles represent neurons. And the circle at the end of neuron number 3, by the way, represents an inhibitory synapse, while the other ones are excitatory synapses. Inhibitory synapse, they imagined, would be like a knot operation, a logical knot. So this is, they're writing on the bottom in their kind of rather quirky notation what the logical operation would be that is carried out by the little 3-neuron neural network on top. And this is what they believe brains are doing. Brains are doing logical calculation, using logical predicates and just carrying out this kind of logical inference. So when they say a logical calculus of the ideas immanent in nervous activity, they mean our brains are logical computers, and neurons are logic gates. Now, the reason this paper was so interesting is, well, you might notice, by the way, that the symbols we now use for logic gates, that's like a NOT gate on the bottom, that little loop on the end that indicates a NOT in a logic gate, I'm pretty sure that comes from their neuron symbol. So like literally logic gates are actually drawn like pyramidal neurons. This is an early cyberneticist, Louis de Couffignol, French, from a book in the early 1950s showing a logic diagram, as one might draw it in a computer. And he just says, well, pretend for a second that that instead of drawing it like this, we just make all of the lines curved, and now notice this looks just like a neural net. So he draws a direct analog between that and the diagrams of neurons that Santiago Ramón y Cajal had drawn from microscope images 50 years earlier. So this is making a very direct connection between neural nets in the brain and these logic circuits. Well, it turned out that this is not how neurons worked at all, and we figured this out starting in the late 40s and early 50s, and this is how neuroscience and computer science diverged. So it turns out that neurons are not carrying out logical operations; they're doing something much more squishy and complex. But basically, this paper of McCulloch and Pitts ended up being the seminal paper of computer science. And this is how all modern classical computers are made, out of logic gates like this. So they basically are neural nets, but they're neural nets of the kind that McCulloch and Pitts imagined, rather than neural nets of the kind that actually exist in our brains that carry out, so computers are neural nets that carry out logical operations. They're fixed, they don't learn. So most AI researchers throughout the 20th century continued to chase this idea, this fantasy that thinking that intelligence could be brought about by logical operations, despite the fact that we had already found out that brains don't work that way. And I believe that was the cause of a lot of these kind of repeated failures in AI winters that went all the way from the 1950s through the early 2000s. People like Marvin Minsky in the AI field, people like Noam Chomsky in linguistics, and many others, all partook of this idea, which is now called good old-fashioned AI, that by doing logic and by calculating, we could achieve intelligence. And I'll give you some examples of how this goes wrong. But yeah, this is all now called good old-fashioned AI. I do want to give props to Alan Turing in this, who actually thought about both ideas. He both thought about good old-fashioned AI, kinds of classic computation, and he also thought about neural nets that learned, that didn't carry out logical operations. So he sort of saw the brain-like path from the start, from the late 40s, and it's a pity he didn't live to see how this all played out over the coming decades. Anyway. There was so people like Marvin Minsky and his colleagues, basically the group of people who invented the term artificial intelligence, all got together in a famous conference at Dartmouth in 1957. And that was the conference at which the term artificial intelligence was invented. And they were like, we haven't made much progress yet at getting computers to do everyday things like understand speech or recognize text or generate convincing language or be able to recognize visual things in the world. We bet we can figure this out, in a summer. Let's get together and see if we can make significant progress, over the course of summer 1957. Of course, they didn't make much progress in the summer of 1957. They did get back together, the ones who are still alive, in 2006. So on the 50th anniversary of when this conference was conceived, and had to acknowledge that in 50 years, very little progress had been made toward AI. Of course, computer science had advanced tremendously. We now had computers that could calculate the trajectories of things in space, and we all had, even in 2006, more computing power in our pockets than existed in total in the world 50 years earlier. And in terms of classical tasks of spreadsheets, of orbits, of Mathematica kinds of stuff, we could do things that were unimaginable 50 years ago, but none of it had actually moved us any closer to anything that we would recognize as intelligent behavior. And these old men had to admit that they hadn't made any progress, and actually all of them had different ideas in 2006 as to what would yield progress in this direction. So it was still very unclear in 2006 what might work. Rules-based processing for natural perception looked pretty hopeless. I want to pause and explain why it's so hopeless. And so you all, I assume, recognize that this is a bike. That's a really, really simple and basic thing that we do every day. We look, we say bike. Now, if you're a rules-based AI person, then you will try to come up with a bunch of principles that you can write down as to how it is that you recognize a bike. You might say things like, well, a bike is a thing that has two wheels, and it has a chain, and it has pedals, and it has handlebars, and it has a seat. The trouble is that there are so many ways of subverting that idea about bikes. What if it has training wheels? Now it has four. No, it's still a bike. What if it has a trailer attached? Still a bike, no problem. Well, what if it's a motorcycle? It has all those things. No. Motorcycle has a motor. That's no longer a bike. Okay, what about an electric bike? That has a motor, but still a bike, right? Oh, okay, that's confusing. What about a tandem bike? What about a picture of a bike in which some of the parts are visible and some are not? Right? We have no problem with all this kind of stuff. We recognize intuitively what a bike is, and yet, any attempt to write down a set of logical rules or principles that would allow us to recognize bike or not bike will fail. And that's why a lot of the classical vision-based systems that attempted to do exactly that just came to naught. We can look at pictures like these, and they might make us kind of laugh, because we both recognize that they're all bikes, and we recognize the ways in which they're funny, right, in which they violate our expectations about bikes. There's something quite profound in that, right, because it means that there is some bikeness, some gestalt of bikeness that we recognize, and that we cannot cast into a set of rules, because no matter which rules we break, we still recognize that the bike is there, as well as recognizing the violation, right, or the weirdness of the bike. Riding a bike, by the way, same kind of thing as recognizing a bike, no rules for it. All of this kind of reminds me of one of the most famous Supreme Court rulings from the 60s. This is from Jacobellis versus Ohio, a ruling by Justice Potter Stewart about whether a racy French film that was making the rounds at the time violated the US's fairly provincial decency laws. And this is where the phrase, I know it when I see it, comes from. He says, yeah, I can't define what pornography is in any kind of legal terms, but I know it when I see it. So porn, just like a bike, you know it when you see it. It's impossible to write down the rules of what is porn and what is not porn. But surely language is easier. So, there are discrete letters and words. They follow the rules of grammar. That's what Noam Chomsky believed. And that led to systems like Eliza, which were attempts to use rules and use grammars to make a kind of AI that would have conversations with human interlocutors. So this is Eliza at work in 1966. And it would have conversations like, actually, I'm going to bring you in, Dr. R, to be the human here in our first dialogue. So I'll be Eliza, the computer. Is something troubling you?
Oh, men are all alike.
What is the connection, do you suppose?
They're always bugging us about something or other.
Can you think of a specific example?
Well, my boyfriend made me come here.
Is it important to you that your boyfriend made you come here?
He says I'm depressed much of the time.
I'm sorry to hear that you are depressed.
It's true. I am unhappy.
Can you explain what made you unhappy? And so on. So this is an example of an Eliza conversational working, which is rare because Eliza doesn't understand anything. And what it's really doing is it's just sort of looking for keywords in your text and using a simple set of grammar production rules to rearrange the words and ask a question. If it doesn't recognize the structure of the sentence that you offered, then it'll ask a random question. People nonetheless got kind of attached, especially to this doctor script in Eliza. But what is interesting about the doctor script is that it was modeled after Rogerian psychotherapy, so-called because it was named after Carl Rogers. Carl Rogers believed in non-judgmental inquiry as a way of doing psychotherapy, and would sort of play this very deliberately sort of naive and non-judgmental role and very questions based in talking to people. And that was actually quite a clever choice for Joe Weizenbaum in making this system. As he put it, this mode of conversation was chosen because the psychiatric interview is one of the few examples of categorized dyadic natural language communication, in which one of the participating pair is free to assume the pose of knowing almost nothing of the real world. If, for example, one were to tell a psychiatrist, I went for a long boat ride, and he responded, tell me about boats, one would not assume that he knew nothing about boats, but that he had some purpose in so directing the subsequent conversation. So, Eliza relied on this trick of Rogerian psychotherapy, but there was definitely nobody home in the Eliza program. Now, it used this idea of grammars, and if you think about natural language and grammatical language, what I'm hoping you'll soon realize is that the intersection of those things, grammatically comprehensible natural language of the sort that Eliza generated, is actually a very small subset of both what is grammatical and what is natural. I'll give you an example. This sentence is grammatical. It's a famous example of a grammatical but incomprehensible sentence. Buffalo, 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 buffalo. Have any of you heard of this one before? It's a bit of a classic AI sentence. So the reason it works is because Buffalo is a city. To buffalo can mean either bully or it can refer to bison, the animal. In the last case, the word is also its own plural. So buffalo is the plural of buffalo. So you could rephrase it, buffalo bison, that other buffalo bison bully, also bully buffalo bison. That's what buffalo, 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 buffalo can be interpreted to mean. So it's a grammatical sentence. It's a perfectly grammatical sentence.
So we have a couple questions.
Please.
We have one from Tanae, which is, what does optimizing utility mean in practice? In a neural network, for example, does it involve mathematically optimizing for particular conditions set by the engineers, or do they augment the data sets or something else?
Yes. So when we optimize for utility in a neural net, that means that we have set some kind of score for how well it performs, and we literally take the derivative with respect to that score on some set of training data, and minimize the loss or maximize the score equivalently. So yes, I mean, one of the things that I am maybe not that quickly working up toward here is that not only classic AI, but also new neural types of AI are always about optimizing some kind of utility, and we can see some of the problems with optimality of utility. We know that humans are not optimizing for anything in particular, based on all of the evidence that we see in psychology experiments, but also based on the fact that we are collectives. Individuals are parts of larger collectives like companies like Google or organizations like SSP, but also our brains are collectives of neurons that all have their own goals and so on, right? Remember that we are just colonies of cells that started off with their own impulses and things. So it's kind of turtles all the way up and all the way down. But yes, optimization is the way almost all machine learning is done today, with some notable and interesting exceptions. The other question?
Yes, we also have a question from Antara. She asks, since computers are essentially neural nets, can we consider computers a new kind of entity? Does a neural net need to be attached to some kind of body or collective to be an entity?
So it's a good question. First of all, neural nets. Yeah, so computers are neural nets. That's right. Although I've also been trying to distinguish between two types of neural nets. There are neural nets that are fixed, sort of that work like classical computers, where the individual units are logic gates. They're wired up in a pre-configured way, and they execute the same set of logical operations every time. So this is neural net in the sense that McCulloch and Pitts thought the brain was, but the brain isn't, and that modern computers all are. Yeah, it's a neural net, but it doesn't work the way a brain does. A brain-like neural net, which is one of the kinds that we can simulate with such computers, but that learns and that has weights in it, or synapse weights that sort of sum up inputs and threshold them and then output. those are a lot more similar to biological brains in that they learn and they're not really carrying out logical operations exactly. I think that both of those can absolutely be entities, even if they're not hooked up to bodies. I mean, they're certainly hooked up to human culture in one way or another. And the larger argument that I'm making here is a relational one. I think that intelligence is in relationships more than it is in individual things. And if we had ideas before the pandemic about bodies being required, I think the pandemic should have disabused us of a lot of that. Many of us have been staying home and have been, interacting with everybody else on Earth, more or less in an entirely electronically mediated way, not particularly healthy for beings like us, that need touch and and physicality in a variety of ways. But did we disappear? Did we cease to be intelligent during this time? No. And we are increasingly mediated from each other digitally. So I don't buy the idea that bodies are required. Anything else on the queue?
No, not yet.
All right. So this is the 8 buffaloes sentence diagrammed as a sentence. But good luck to you if it makes sense. When you just read it or say it. I'd like to now give you another example where it's not possible to separate grammar from meaning. So this is an example from neural translation. So translating from English into Spanish, which is one of the things that classic AI using rules believed would be an easy task, right? Because if you can diagram a sentence, then why not diagram the sentence in English, replace the words with their equivalent words in Spanish, say, and then put the sentence back together using the same diagram, right? Seems like it ought to be straightforward. It's not straightforward. And this is an illustration of why. I broke the ball and had to get it repaired. Very simple sentence. In Spanish, that's rompí la bola y tuve que repararla. Now, Spanish is a gendered language where English is not always. So bola is feminine, and that means that repararla, repair it, has to end with la. It's the feminine version of the verb. By contrast, I broke the violin and had to get it repaired, is rompí el violín y tuve que repararlo, because violin is masculine. All right, so we have repararlo instead of repararla. All right, so far so good. How about I dropped the bowling ball on the violin and it broke. I had to get it repaired. Now, can anybody tell me what had to get repaired? Is it the bowling ball or the violin?
The violin.
Obviously it's the violin, right? If you're translating this, it will never even occur to you to think that this is grammatically completely ambiguous, right? It could refer to bowling ball or violin, but that will not even cross your mind as a translator, because we understand the common sense physics of violins and bowling balls. So yeah, the correct translation is dejé caer la bola de boliche sobre el violín y se rompió, tuve que repararlo. I had to repair it, masculine, because it refers to the violin. Nobody would ever translate this repararla. That would cause people to do a double take. Wait, violin is masculine. What do you mean what do you mean repararla? So this is a case where even the most simple grammatical thing requires that you understand the common sense physics of bowling balls and violins, and there is no grammar system that will resolve things like this. So this is sort of the death knell for for the idea of grammars in the sense that computer languages have, for example, working to do natural language processing tasks in human languages, and there are many such examples. This is just an easy one. So all of this led to learned representations, which we've already started talking about in response to your questions. Right after that that sort of reunion of the old AI guys in 2006, learned representations began to really come into ascendancy, mostly with neural nets. Hubert Dreyfus, who wrote a really nice critique of good old-fashioned AI way back in 1972, What Computers Can't Do, a critique of artificial reason, wrote, "The view that the brain as a general-purpose symbol manipulating device operates like a digital computer is an empirical hypothesis which has had its day." He believed it had already had its day back in 1972. "Insofar as arguments from biology are relevant, the evidence is against the possibility of using digital computers to produce intelligence. Even if the brain did function like a digital computer at some level, it would not necessarily provide encouragement for those working in computer science or AI. For the brain might be wired like a very large array of randomly connected neurons, such as the perceptrons, proposed by the group Minsky dismisses as the early cyberneticists. Such a neural net can be simulated using a program, but such a program is in no sense a heuristic program, meaning it in no sense follows rules or carries out logical inferences, even though you can write a program that will just do tons and tons of additions and multiplications to simulate one of these neural nets. And that's indeed how we do simulations of neural nets today. We're still running them mostly on classical computers, but there's no logical calculus going on. It's just a simulation of something that itself is doing something a lot fuzzier, and which is designed to optimize a function, as you all have pointed out. That lineage goes all the way back to at least to Frank Rosenblatt in 1959, who made the first artificial neural network, the perceptron, which he was able to train to do very, very simple tasks like distinguishing triangles from circles from squares. It was kind of a one-layer neural network that involved this nest of wires connecting a grid of photoreceptors. There's like 20 by 20 photoreceptors to a handful of outputs. And there were these potentiometers or dials on each of those wires, on each of the synapses, driven by a motor. And he implemented a simple rule that would tune the motor this way or that, depending on the error rate, on getting the right answer. So that was optimizing a simple utility function for correctness of the classification. Now, the one layer of weights that Rosenblatt used can just do template matching. It's really, really simple kind of operation. It'll basically just be able to recognize a handwritten digit 8 by having those weights sort of look like the average 8. And that means linear separation. You can only do so well with linear separation. But there have been theorems proved since that show that if you have 2 or more layers of weights, so if you start to have a deep neural network, then any function whatsoever can be modeled, and one can use optimization to model anything whatsoever. Now, Google has played a pretty big role in this whole sort of neural net revolution, because in order to do a good job of this, you generally need to do a lot of computation, and you also need a lot of training data, and Google has had both in spades. Big computation, because it's been running these kind of gigantic data centers for a long time, and lots of data because it has been running lots of online services that generate tons of data and that index the entire web and so on since the late 90s. And I think that's why Google ended up playing quite a prominent role in the sort of modern neural net revolution, and has started to make chips like these TensorFlow chips that are specialized for simulating neural nets at very, very high speed. Now, I think personally that most machine learning in the future is going to be done on really small devices, not in giant data centers like this. And that may come as a little bit of a surprise, from somebody working at Google, but I will point out why. So first, I'll note that even way back in 2016, our team was running neural nets for doing things like recognizing animals on phones, which you wouldn't necessarily think have the fastest processors, but neural nets trained to recognize different species of birds are running here in real time on the phone's processor. And when you think about the number of additions and multiplications that are needed in order to simulate a neural net of this size, it's actually quite staggering that phones can do all of that. But that's really all a consequence of Moore's law, which I'm sure you all have heard of. Just before the invention of the integrated circuit in the 1960s, a simple 4-function calculator required 13 circuit boards stuffed with components like the ones that you see, super unreliable and very heavy. By contrast, a Google Pixel 3 phone in 2018, when you tear it down, looks like it has almost nothing on the inside. The main parts here are a foil shield for static and a large battery. This L-shaped board is where all of the electronics are. There's almost nothing inside because everything has shrunk away to nothing. Even when I was using my first laptops, those laptops were stuffed with circuit boards the same way that 4-function calculator was. Nowadays, the entire circuitry of the laptop is on one of these so-called systems on chip, or this is a system on module. So it's very, very small and has a Snapdragon, which is was a couple of years ago one of the fastest computers for for personal use in the world. And basically that's how we get these extremely thin laptops that we have nowadays. They're almost all battery on the inside. The actual business end of it is no bigger than a phone. That is than the little L-shaped board on the inside of a phone. Memory is an even more dramatic story. We now have to have multiple adapters in order to turn memory like this 64 gig micro SD into something that plugs into something that can fit into your computer. 64 gigs is small nowadays. I made this slide 2 years ago, but now there are 1 terabyte memory chips of the same size. And just to give you a little bit of a sense of how much this has shrunk, this 512 gigabyte micro SD card, which has a weight of roughly 1 gram, and as I say, it's now obsolete. We can compare that with the first hard drive. This is from the 1950s. It required forklifts to get out of the plane, and using if we put hard drives of that sort all over Husky Stadium at University of Washington like this, 1/4 of a mile on a side with these IBM 350 hard drives, that would be 512 gigabytes, and God knows how much energy that would all use. So the number of orders of magnitude that things have shrunk since the 1950s is just kind of mind-boggling. The weight of that, by the way, would be 150,000 tons or 136 billion grams. So for memory, we've had 136 billion fold reduction in size since the 1950s. And there's still plenty of room at the bottom, by the way, to use Richard Feynman's phrase. Even assuming no further linear gains in scale, we're barely using 3D structure at the moment. And if you imagine using current technologies and filling up an entire sugar cube with transistors, that's easily a petabyte of data, which is Feynman's estimate of the information in all of the 24 million volumes or books of interest in the world in 1959. So nanotechnology, in other words, which Feynman envisioned in the 60s, has already quietly arrived, and it's living in our pockets and our purses, even though we're still very far from robotic nanotechnology of the kind that he imagined. And I'm sure you've all seen many diagrams with logarithmic y-axes of these kinds that show the increase in computing power over the years. This is a slightly fancier version of one of those Moore's law diagrams, showing that something began going a little weird in 2006 with Moore's law. Many people have talked about the end of Moore's law. What started happening in 2006 is that we stopped being able to continue to crank up the clock speed of transistors. So, you all are probably a little bit too young to remember the days in which the number of megahertz and then gigahertz that a computer was running was sort of a relevant figure of merit. That number kept going up every year. That stopped happening around 2006. And that's why we began getting increases in the number of cores on a computing chip around that time. Because if you stop being able to make the computer faster, then you start putting, we're still getting more and more transistors on a chip. What else can you do? Start putting more and more computers on the chip. But the thing is, if you're doing classical logical computing, it's actually quite hard to know what to do with all of those cores. Because if you're running a program of the kind that you all write, right, that's designed to run a sequence of instructions in order, so what if you have more computers, right? You can't do any more than you could with one. But the thing is, neural computing, which involves lots of different artificial neurons being simulated in parallel, we know exactly what to do with lots of transistors in that scenario. And so my informed guess is that over the coming years, we've already seen a kind of plateau in classical computing just on the basis of this kind of transistor scaling. But all of these extra transistors are going to keep getting used for neural computing, and neural computing is still very much exploding even as classical computing has plateaued. So yeah, what I think all of that means is that if you follow this out by another decade or two, we are going to basically be completely dominated by neural computing, and the amount of classical computing happening in our personal devices will be a tiny fraction of the transistors in there. This is what sort of parallel computing buys us today. So this is now 3 years old, but Google's Edge TPU runs 4 trillion operations per second at 2 watts in this little tiny chip, and can run a neural net for doing the kind of image recognition that I was just showing earlier at 400 frames per second. And this is now 3 years old. The performance has gotten much better in the 3 years since. So I'm going to skip some of these points, although I do want to note that the idea that neural nets of this kind can be run in chips that are very small and very low power is, I believe, extremely important for privacy purposes. So if we want to live in a world in which AI is being used to interact with us all the time, or is embedded in the environment to be able to estimate the lengths of lines in an airport or whatever, it's a good idea to build such systems in ways that don't involve all of that data going to the data center, because then you've built a massive surveillance system, which can be repurposed to do all kinds of very unpleasant things. Whereas putting the intelligence locally on those devices means that they can act more like social actors in the world today. More like public officials or service dogs or other kinds of animals, or institutions or beings, right, that are embedded in the social fabric, as opposed to creating something giant and centralized. All right. Is there a question? Sorry, is that beep? Okay. So I know I'm a little bit all over the place here, but I want to mention something about training these neural nets that now that we're on the topic of privacy, which does connect with ethics, of course, that I'm something that our group has done that I'm quite proud of, called federated learning. So the fact that so much data are needed in order to train a neural net, and that the reason Google had all of this data and has been at the forefront of AI is because of running everything centrally for many years. That actually bothered me quite a bit, and was one of the reasons that I joined the company in 2013, to think not only about how neural nets can run on small devices that are embedded on our persons or in society, but also how neural nets could learn from data in a decentralized way that doesn't involve surveillance, that doesn't involve all of that training data being collected in the data center. And we figured out how to do this. It's called federated learning. So to give a very simple example, the neural nets of the same kind that Frank Rosenblatt was working on for distinguishing between a small handful of different sorts of things. This is one of the classic ones called MNIST, which is all about distinguishing handwritten digits 0 through 9 and recognizing which digit it is. This is what the training data for that looks like. Repeat by many rows, right? And this is all data that was collected by the National Institute for Standards and Technology from a bunch of forms given to employees and also to high school students. So in federated learning, the training process, rather than collecting all of that data in one spot, involves leaving the data wherever they live. So if that handwriting or the speech for speech recognition or whatever is on your own device, then the data never leaves the device. Instead of collecting all the data at the server and training a giant neural net there, you distribute the learning process out to all of the devices. So this is called federated learning. There's actually a comic about it that we made a couple of years ago that you can look up. So if you look up federated learning comic, you can learn all about it. But the idea is that on each device, when you leave it plugged in at night, it sort of runs over the data that it has seen throughout the day and adjusts the weights of its local copy of the neural net. And then it can take those adjusted weights and compress and encrypt them and send the adjusted weights rather than the training data to a server. And if you use something called secure aggregation, which is a cryptographic technique, then you can basically make it so that only when you combine lots of people's contribution together, hundreds or thousands of people's contributions together, can the sum of all of those changes be read out. And then, the sort of global copy of this neural net is updated and sent back out to all of the devices. So this is a way of creating a system that can learn from examples out there in the world on many people's devices, or in many devices embedded in a city or in a piece of infrastructure, without creating the sort of privacy nightmare that comes from surveilling all of the original data. So it's something that I'm pretty excited about. It has really skyrocketed in the last couple of years. There's an exponentially increasing number of papers on this topic now, and there's a lot of work, especially on the use of this for healthcare, where healthcare records are very private, but there's obviously a huge amount of value in learning collectively about the interactions of drugs or the course of disease or all sorts of other things that one might want to use AI for doing. So that's federated learning. I guess I didn't sort of finish the story about. Sorry, please.
We have some more questions. So yeah, we've got another 2 questions, I believe, for you. Or nope, now we have 3 more questions for you. So first one is, when do you think we will have something like the person of interest machine? If you don't know the movie, the machine predicts future crimes.
That's a really interesting question. I mean, so predicting crimes, is something that we have to be super, super careful about, because there have been a lot of neural nets that do exactly that sort of thing, already made so far, and they're extremely problematic. All right, so I would encourage whoever asked the question to Google an essay that I wrote with a couple of collaborators called "Physiognomy's New Clothes." It was a response to a Chinese paper from 2016 that claimed that from nothing but a facial picture, nothing but a sort of picture of your face from your driver's license, that criminality could be predicted with very, very high accuracy. Now, it turned out, to make a long story short, that what was really being modeled was all of the racism and bias built into the criminal justice system in China, which, by the way, this is not a unique property to China. It's the same here, right? Tell me your zip code, your race, and your parents' income, and I'll tell you the likelihood with which you are quote unquote a criminal, meaning put in prison, right? And I will probably do a better job of predicting that, than even a trial judge. Actually here's the details of a case. Does that mean that that's fair, or that that's a good thing for us to do? No. I actually think that AI systems that analyze correlations between things like criminal judgments or credit ratings or whatever, and all kinds of other variables about demographics are really important. Most of all as diagnostics for understanding all of the ways in which humans and human society is biased, as opposed to actually predicting crime. But this is a large and complex topic, so probably deserves a little bit longer an answer. But yeah, you could begin with that article, and it has lots of pointers in it. There were other questions.
Yep. So our second question is, what impact can you see quantum computing having on neural nets?
I don't know. So I'm friends with Hartmut Nevin, who runs Google's quantum computing group, and we've had a lot of debates about this. Hartmut originally contended that that maybe brains use quantum in some way to think. That idea has, I think, been pretty widely discredited. We don't believe that neural nets in people use quantum effects in any meaningful way. I mean, obviously, all of matter relies on quantum mechanics. So I'm not saying quantum doesn't you could not take the quantum out of a brain, but it's not using uncertainty or superpositions or anything else in quantum mechanics to do thinking, as far as we know. So I don't know. I mean, there are some ideas that maybe quantum optimization could allow learning to happen faster, but I'm personally not convinced. I think it's still very, very early in quantum computing. We don't really know what it's going to be useful for yet. I haven't heard any stories that sound to me compelling as yet. Not only in neuroscience or AI, but actually at all. And cryptography is probably the closest. But it's still wide open. I don't want to say it's useless, but I think it has not found its magical application yet. Was there another?
Yes, our third question is, do you think that the decentralized learning on local devices may improve AI simulating humans on an individual scale, in that
Absolutely.
the devices have their own neural nets?
Yeah, absolutely. Both for the idea of localizing and personalizing those nets and making them kind of situated as opposed to global, and in terms of being able to learn from situated and local conditions that we would be very uncomfortable gathering together in one spot. So even with the digit recognition example, which is really trivial, people write digits in different ways. I mean, if you're European, you put a bar through the 7, and the 1 looks a little bit like the American 7, and so on. If you use federated learning and federated personalization kinds of approaches, then all of that can be, all of those variations worldwide can be learned in ways that a sort of more centralized surveillance kind of approach would have a hard time doing, because it generally can't sample from everywhere. Your individual local copy can adapt very quickly to what you're doing, and so basically the kind of collective neural net becomes a local expert of all sorts of things, as well as being able to adapt very quickly to local conditions. So yeah, I think that's one of the more exciting aspects of that. It's not just about privacy; it's also about variety. Anything else in the queue? Okay, I'm conscious that, so we're running very low on time, I think. So I'd like to skip ahead because I prepared way too much material here. But I'd like to skip ahead to.
We actually, Blaise, I'm sorry, but I mean, we have until 12 noon our time.
Oh, wow.
So
okay.
We have another scheduled, say 40 minutes, 35 minutes if you need. Okay,
great. Well, I mean, I'm also conscious of not being boring, but let me in that case go somewhere in the middle, and skip to some things that are very much in the news right now, and that I think may connect together a lot of the themes that I've been touching on, which are fairly far flung. So I think I've already said that I believe that the vast majority of transistors in our devices are going to be neural. It also follows that their power requirements are going to keep going down and down for a variety of reasons that I'm not going to go into. But I believe that will mean that most of them run on ambient power, meaning just parasitic power from the difference in the temperature between your skin and the air, and movement that you make and light that falls on the devices and so on. And also that the majority of neurons that you all have by the time you are 50 years old will be implemented in silicon, as opposed to, or something like silicon, as opposed to in wetware. So we're all headed for a pretty dramatic kind of cyborg transformations, I believe. Although in many ways we already are cyborgs. So this is in some sense nothing new. But let me skip to something that is going on right now that you may all have heard about in the news. So a lot of the newest developments in neural nets do go beyond the idea of just passing a test or minimizing the error or maximizing the score on a fixed function. They are going beyond utility, and And they also are starting to incorporate the ideas of attention, which is something that we know is very important in biological brains, and emerged soon after we started to have complex brains 350 million years ago. So going beyond utility is something that that a lot of unsupervised so-called learning techniques do. Unsupervised learning is when you don't have just a set of known results, like here is a picture of a 2 and the correct answer is 2. And the goal with the neural net is just to optimize the score. But instead, you just have a world, whether that world is a video game, or that world is all of the text on the internet, or a trillion documents on the internet. There are these new methods for doing unsupervised learning. Just learn from the data without any assumption about what to do with it. They're essentially learning all of the statistical regularities in that data, which is I believe a little bit more like what we do as kids. We experience the world. Of course, we have emotions, we have drives, we have social rewards, but we also are just taking in a lot, and we're learning a lot passively by just being in the world and experiencing it. And these attention-based unsupervised neural nets have started to do the same thing just in the last few years. And when we then have conversations with them, for instance, with neural nets that involve large language models that have learned from lots of text on the internet, the conversations start to get very, very convincing. Let's just say this is like it's sort of like we're reviving the Eliza idea of Joe Weizenbaum, except now with an entity where I think it's a little trickier to say whether there's somebody home or not. So I will read a couple of if Dr. R, if you are still around to do dialogues with me, we could try a couple of real ones that are not cherry picked. So these are just these are typical, unlike the Eliza conversation that we had earlier. With Lambda, which is Google's giant unsupervised language model. Do you want to begin and be the user?
Sure. So I dropped a bowling ball on the glass table and it broke.
How did a bowling ball end up on your glass table?
Never mind that. What broke?
Apparently the glass on the table broke. Did you know that glass can be recycled?
Let's say instead that I dropped a glass bowling ball on the stone table and it broke.
This is a very interesting situation. Glass and stone are both hard surfaces, and glass is supposed to be the material of the future insofar as it can be recycled infinitely. Stone, on the other hand, is a very old material, but is indestructible by nature.
So in this case, what broke?
I suppose I'm going to go with the ball being the thing that broke. Glass is much more fragile than stone, and it seems like it's quite likely that the ball would break under the laws of physics. So that was my just when I tried to pose that sort of bowling ball and table or violin and bowling ball or whatever kind of question to Lambda. This is the conversation that ensued. It's really interesting because it shows you that common sense physics, right? I mean, somebody asked a question earlier about whether whether the ideas of no, sorry, no, I'll drop that train of thought. The fact that Lambda is doing something much more than just understanding grammar or aping it, right, is manifest in this conversation. And in particular, even though it hasn't experienced anything like the physical world, right, it hasn't held a bowling ball or shattered glass itself, it has read all about these things. And having read all about these things, it's learned how those materials behave. This idea that you have to be embodied, that you have to have a body and experience the physical world in order to understand things, I think is obviously false. I mean, you can look at Helen Keller writing about visual and auditory phenomena and see that that's not the case. You can consider people who write about places that they've never been, right, or write fiction that involves characters that they aren't. And you can see that that's not the case. That's not the case for a language system like this one either. Here's another one. Dr. R, please. Oops, sorry.
Sorry, muted. I started. Buffalo, 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 buffalo.
That's interesting, but what can I do for you today?
Did you understand that sentence?
Sure, I did. Let me know if there's anything else you need my help with.
Okay, what did I say?
You told me that your goal was to make friends, which I can help with.
No, I said buffalo, 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 buffalo.
All right, now I understand that you would like me to explain that tongue twister to you. Buffalo, buffalo, that other buffalo, 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 also buffalo, buffalo, buffalo.
But what does it mean?
That tongue twister means that a group of buffalo, buffalo, also known as bison, bully a group of other buffalo, buffalo, which also happen to bully the first group of buffalo, buffalo. It's a confusing statement to make, as the reader may have trouble understanding whom is doing the bullying. Now, the reason Lambda understood this is because it's read a whole lot of the internet. And this is a famous tongue twister. So, it's basically relying on, expertise that it has learned about this.
Could I ask a follow-up that's not on the list at the?
Yeah, we could totally try that on my other machine.
Oh no, I didn't mean asking. I meant asking you a question.
Yeah, sure.
Was this spoken, or did the AI see that some of the buffaloes were capitalized?
This is typed exactly
okay.
as written. So yeah, it's not done with a with spoken language. Although we do have spoken language versions of it as well that do speech synthesis, speech understanding. I don't think it would make any difference in this case. Although you're right that which buffaloes are capitalized is part of the is part of what helps you disambiguate the meanings of the different buffaloes. But it's not doing a grammatical analysis, though, is the thing. It's just like recognizing this tongue twister. And in fact, you can see some, one of the little Easter eggs here, I suppose, is that whom is doing the bullying, right? That very last sentence, that is not actually grammatical. It should be who is doing the bullying. Whom is the object, not the subject. So, even the idea that this is like a Mr. Spock or Data type, perfect, perfectly rational, logical, flawless, being, not the case at all. I've actually had conversations with Lambda in which there are misspellings in the responses, as well as wrong grammar. It's a neural net just like us, and makes all the same kinds of, quote unquote, irrational mistakes.
Thank you.
But it has all kinds of common sense knowledge too. So yeah, it's Eliza by neural net. It passes the Turing test for many, I would say. It is a cortex-like general intelligence. That's my belief. It's controversial. It's able to do improv and to socially model emotion. It's unsupervised. It's capable of one-shot learning and trained for believability. It isn't embodied. It isn't goal-directed. It's not endowed with the fixed personality. It's not reliable. There's still a lot of, there are a lot of things that it still can't do. But I think we're at a real, when I began to interact with language models like this one, I have to say, like, I and a bunch of my colleagues and a bunch of other people in the community are starting to get this really spooky feeling of like, okay, we've kind of arrived. We now have not only neural nets that can recognize objects and things, but that have a lot of the hallmarks of general intelligence, and it starts to beg all sorts of questions, I would say. So yeah, we should open it up to discussion now, because I think there are implicit connections among the various different things that I've gone into over the past hour and a half, but they're probably better for talking through than for me continuing to blab
on. We have a couple of questions lined up. So first, when we do eventually have a completed AI, what do you think would be the purpose/use for it? Would its benefits outweigh any existing risks?
Yeah. So first of all, asking what is something for, which is like the teleology type question. What's the purpose of it? What is it good for? I think is a fairly complicated question because, in a way, it presumes that everything is for something. And like, what is a cat for? They're like basically good for nothing, right? What is a person for? Most people are not really good for something either. We're actually I believe starting to face a reality that the idea that people are for something, that their work or their labor is their value, is it's actually quite a modern and Western and sort of post-industrial revolution kind of idea, and it's one that puts dignity and value and so on I think a very flimsy footing, because it basically says that the moment you make a machine that can do the labor that you've been compensated for doing with money, then you become useless. That's worrisome because we're certainly in an era now where the majority of people, in the developed countries, are doing information work, I'm not sure there's very much information work left that is unattainable for for neural nets. So my own belief is that I guess we need to be rethinking these ideas about value, and in a sense, well, there's a book that I read last year that for me was very influential, and now we're going a little bit far afield, but it's by an anthropologist who just died sadly in the fall. David Graeber died quite young. He was very influential. He was actually one of the key movers behind the 99% movement. We are the 99%, Occupy Wall Street, and so on. This book is called Bullshit Jobs. And if you'll excuse my language, he said most jobs are one of two types. They're either bullshit jobs or shit jobs. The difference being that a shit job is one that is essential, like being a janitor or a teacher, and is inevitably very poorly paid, in the US especially. And a bullshit job is one that people in bullshit jobs know that the world would be better off if they weren't doing what they're doing, but they will never admit it in public. And he has sort of a series of estimates about like exactly what proportion of labor is bullshit jobs these days. And I guess spoiler alert, it's a lot. His basic thesis is that Keynes, the economist in the early 20th century, imagined that with automation and with the development of technologies of all sorts, we would all be working 15-hour work weeks by now, by the early 2000s. And basically Graeber is saying he thinks Keynes was right, but rather than that actually having taken place, we've just invented a bunch of bullshit jobs for the middle and upper middle classes to do, and essentially have enacted a form of socialism for the rich by doing that. So food for thought. Other questions?
We also have a question from Tanae. What do you think about the ethical implications of unsupervised learning versus supervised learning? Is one more susceptible to training data or human bias than the other? And how do unsupervised models converge without a goal?
Yeah, both really good questions. So first on the questions about bias. Yes, so bias is rampant in in every form of machine learning, whether supervised or unsupervised. When it's supervised, then the biases come from the labelers, you might think that means that you can do a better job, by controlling your labelers more, or something. But it's actually really, really hard because, if your data set is large, in order to train a large model, then you need lots of labelers. And then you need to think about who those people are, and and their biases will creep in many ways. There was, even for doing something as simple as image labeling, biases of all sorts creep in. There's some great work from a couple of years ago called ImageNet Roulette that shows all of the extreme biases in ImageNet labeling. And image recognition is child's play compared to a lot of the new kinds of AI that make other sorts of more sophisticated judgments or interact with language, what have you. And unsupervised learning is also susceptible to it's not just labelers, it's whatever it encounters, right? It's biases there in all of language out there on the internet, bias of all kinds. There was a famous case a couple of years ago of translation. I gave some examples of gender in translation in the talk. Turkish, it turns out, is a gender neutral language with respect to its pronouns. And so, for example, they are a nurse and they are a doctor are sentences in Turkish. And if you translate that gender neutral they like pronoun sentence into English with a normal neural translator that has just learned on all of the text out there on the internet, then it will translate it as he is a doctor and she is a nurse. Now, the reason is that most of the time when in English somebody says pronoun is a doctor, it is he. That's why there's that famous riddle about the mom doctor who can't operate on her son, and nobody knows that it's possibly a woman. I look up the riddle if you haven't heard it. So those are biases in language, and they're biases in cognition, and they're out there. There's no difference between a bias like that one and understanding that that a glass bowling ball is likelier to break than a stone table. Those are both statistical regularities, and there's no difference. The only difference is that in one of these cases we have ideas about what we would like to be that are different from what we are. We have moral ambitions, if you like. So the idea of moral ambitions is something that one can talk about with a large language model, where one can't have those kinds of conversations with a simpler model. So my own belief is that the route to better ethics in AI does not come from from trying to control the supervised learning with small models, but rather from training very, very large models with everything out there in the same ways that that we experience, and then having moral conversations that are transparent with those agents, in which we actually assert what it is that we want. It forces us to come to grips with what it is that we want and make that manifest. And of course, those statements are controversial because, as I talked about with respect to impossibility of voting theorems and so on, it's not like there is one set of that like there is some right that everybody agrees on, right? So it's actually very hard to come up with a core set of values that enough people agree on that we would be okay to just say what they are, and you have to acknowledge that whatever AI you make like that is aligned with the values of certain groups, certain people, certain ideas, and not with others. And I think drop the concept that there's somehow a universal, unbiased good living out there somewhere. There isn't. It's all politics. So I know that's maybe not a very satisfying question, but it's I think it's complicated.
We also have a question from Ram. He asks, how did your studies in computational neuroscience impact your work in AI?
Great question. So so one of the ways is that I was always, so my wife is a computational neuroscientist as well, and we've had a lot of conversations over the years about as neural nets have started to become dominant, what aspects of artificial neural nets are actually consistent with the real biological neurons, and which ones are still cartoons, and are those differences important? And in many cases, I think the differences have been very important and have pointed the way toward more sophisticated iterations. I mean, many of the big developments in neural nets over the past 20, 30 years have actually been done by people who span both fields, who are also computational neuroscientists. Attention is just the latest example, I believe. I mean, attention is is something that is biologically inspired in the same way that that convolutional nets are biologically inspired by things in visual cortex.
If we have time, I'm gonna mush a couple questions together on our queue. Katrina wanted to know at what point can AI start developing morals rather than following ethical codes? Like, can AI understand ethics and morals by itself? I think that's the question we're trying to get at. And then Amran wanted to know if AI can learn to be selfish when it's made to serve human needs.
Yeah. So to tackle the second part first, any kind of system has to be coupled to not necessarily to a specific goal, because chit chat, right, of the sort that we've just seen in those dialogues, is not actually goal directed. It's really just designed to be plausible, designed to be believable, designed to make sense. So the goal, if you like, is to be indistinguishable from what a person might say. But the question then becomes, well, what do you tell such an AI to do? How do you align it? If it has read a bunch of Nazi literature on the Daily Stormer or something, right? Somebody who kind of subscribes to the I would say more old-fashioned view of what AI ethics is all about. It's like, no, you've got to clean all that up. Like, it can't be exposed to that stuff, or it'll be biased by Nazis. I think that's a little bit like nanny filters on the internet when you raise a child. Like, maybe when the child's really young, you have nanny filters like that on, but you can't really expect moral or ethical maturity to somehow emerge from just failing to expose a child to all of that kind of stuff, right? You would like to be able to say at some point, like, don't be a Nazi, right? And how do you even know what that means, right? If you don't understand what Nazis are. So my own belief is that sophisticated models that include language and culture and understand where we are a prerequisite in order to to make sense of where we want to go from here, right? What is sort of a good direction, a bad direction, and as I've also said, it's not like good and bad direction have some meaning outside of human society, right? I mean, I have very strong beliefs that Nazism is evil, but frankly, I'm a person situated in a social net, in a very specific spot, right? And an attempt to make a kind of reasoned set of reasons why Nazis are evil, I will fail. These are my beliefs. So the idea that we can somehow make a more perfect AI that that is decoupled, simultaneously decoupled from human society and wiser than human society is, I think, an absolute illusion, a chimera. Other questions, thoughts?
Do we have maybe one more question?
I'm not sure if I'm allowed to ask a question, but I was just curious for like the lambda thing or the talking thing. Is there like a demo available, or is that still not publicly available?
It's still not publicly available. Okay. One of the reasons, by the way, is that these models. I mean, well, there are many reasons. I mean, it's still very experimental, and so given how much scrutiny there is on all of this kind of stuff, it is possible to get these models to say, things that are going to get seized on by by social media or whatever is like, oh my God, it's saying something bad. That's part of the reason, but also part of the reason is that these models are still quite expensive to run, and we don't have the computing resources to make it available to everybody who would want to play with them yet. But my feeling is that both of those are very much in progress, right? Computational efficiency is greatly increasing, especially as we dedicate sort of specialized silicon to doing this kind of stuff. And and even though there is no AI that will make everybody happy, the idea of making AIs that at least have clearly articulable values and stick to those and do a good job of it, I think is also we're like definitely making progress there. So yeah, soon I hope, Peyton, but not yet.
Okay, thank you.
I have a question too. I guess it's sort of tangentially related to what we're talking about. But do you have any thoughts on like how AI is used in autonomous cars? I know it's not exactly quite, but it is related to artificial intelligence. So I was just wondering if you have any thoughts on that.
It is, yeah. I think it's a really interesting case because so if we rewind by a few years, the way a lot of us were thinking about this is, there's a sensory system in the car and a motor system for actually like manipulating the wheels and the gas and the brakes, and then there's what's in the middle. There's kind of the decision-making parts in the middle, and clearly on both the sensory and on the motor side, these modern neural net kind of approaches greatly outperform any kind of rules-based approach. So you definitely want to, if you want this thing to be able to, do the best possible job of spotting pedestrians, jumping out into the road and so on, right? Or a dog crossing the road or a car out of its lane, you really want to use neural nets to do this. And neural nets are already better than humans in all of those tasks, for sure. I mean, humans are actually terrible drivers. So the idea of becoming better than a human is, that's not a very high bar, to be honest. The bar that we've actually set, and the reason that we don't have all kinds of autonomous vehicles on the road today, is way higher than a human, which is the only reason that hasn't already happened. I actually think that's a travesty because there are lots of people dying in the meantime, and also the ecological harm of having like very, very wide roads, because humans drift around in the lane all over the place, and they have to park near where they go, which means there's lots of in urban cores, there's lots of surface area dedicated to parking, which is terrible, and traffic lights and the need for various kind of anti-gridlock kinds of schemes. I mean, all of that could become infinitely better if robots were driving cars today. It'd be great for the ecology, and it would be great for saving human lives. But anyway, so perceptual systems we know are much superior with neural nets than with rule-based systems, and at this point superior with neural nets than human perception as well. The same is true on the motor control side of things. Somebody just pointed me to robot dancing video from Boston Dynamics, and it kind of gives a little bit of a sense of, robotics is not great relative to AI, but all that kind of very fine control and balance, sure, machine learned systems can do a better job of that now than people can. The part in the middle, I think a lot of us believed that more classical decision-based logic should still hold for, because we would like to think about traffic and driving in terms of rules, in terms of following certain rules, right? My kids are both learning to drive now, and they have these very specific things that they're rules that they're supposed to follow, and it's like the manual has gotten like 10 times longer than it was when I learned how to drive. But like with so many of these things, when you actually dig a layer deeper in, you realize that the way people drive is not actually by following the rules. And that's not a bad thing. I'm not saying that people are bad and rule breaky. I'm saying that if you literally follow all of the rules, you will be a poor driver, and it won't work socially. I've had a lot of interesting conversations with the kids about like at stop signs, like where do you actually stop, and do you creep ahead, and when, and how much, and like what do you do, right, in order to actually optimize the way stop signs behave. And it's actually very difficult to write down in rules for the same reasons that it's hard to write down in rules the way bikes, the way you recognize a bike, right, or like how you change lanes or how you do various things. So yeah, I think in short that neural nets all the way up and down will do a better job than rules, but then you do sacrifice the things like perfect explainability, in a court, right, when there is an accident, which inevitably there will be, even if it's a lot less common than with humans. You won't be able to say like, here's the stack trace, here is the if and then that was followed, etc., because it'll be like a human brain, like, well, I did what I thought was best at the time. So yeah, that's my own sense. And by the way, in the US, it looks a lot more like following rules than it does in many other countries. Driving in Mexico or driving in India or something. Any idea you have that a rule-based system could do that will go right out the window immediately.
I just had a question, if you don't mind. I was wondering
I hate to do this. I'm so sorry, but I think we're going to have to stop. Okay. It's already 9 minutes till the hour, and I know that most of you probably have a learning block to get to, so I apologize. But I would like everyone to unmute and thank our guest lecturer for spending the last couple of hours with us. Thank you so much.
Thank you.
Thank you.
Thank you.
Thank you so much.
Thank you all. It's thank you all. Very much my pleasure. I know I've been all over the place in the talk, but I hope that we covered a bunch of interesting territory, and I hope you all do really cool things in this field. I think it'll be a huge part of our future. All best.
Just really
thank you very much.
Quick, would it be possible to like put your email in the chat or something in case we come up with like extra questions in the coming days?
Sure. It's
you.
Blaise@google.com.